So welcome back. It's a great honor to introduce a mathematical legend, John Milner, who, as an undergraduate, showed that the integral of the curvature of a knot was at least 4 pi, and became very famous as a result. Won the Fields Medal at the age of 31. Was professor at Princeton and the Institute for Advanced Study, and is now director of Center for Mathematical Research at Stony Brook, and is a recipient of many honors, including the National Medal of Science. We'll introduce the next speaker, Jack Milner.
Well, it's a great pleasure to introduce Vladimir Voevodsky. Voevodsky began his mathematical career in Moscow and then came here to Harvard as a junior fellow, and after a few years at Northwestern is now at the Institute for Advanced Study. And as you all know, he was recently awarded a Fields Medal for his work on Motivic Homotopy theory. This is a marvelous development which introduces ideas and methods from homotopy theory into pure algebra and gives a essential new tool for solving algebraic problems. So it's my great pleasure to introduce Voevodsky.
Hello, thank you very much for thank you, Jack, for the introduction. So I was given by Arthur sort of an impossible task. I was requested to explain Motivic homotopy theory so that it will be understood by non-mathematicians. So whatever came out of it, you'll see now, but I don't guarantee that it will be now understandable by either mathematicians or non-mathematicians. So what there was at first, so at first there were spaces. So mathematicians were studying spaces and starting with simple examples of spaces. So one of the most basic spaces is a point. There is one which is even more basic, but it's hard to draw. Another one is standard space, which I will have to talk about, is a unit interval. So an interval of the real line lying between 0 and 1. The third example here on the picture is some example of a space of dimension 2. It's supposed to look like some baking good with 2 holes in it. So the last example is more sophisticated, and I want to include it here. It's a more sort of mathematical example of a space. It's a space of all n by n matrices with complex entries and with non-zero determinant. That would be a sophisticated space of dimension n, well, depending on how you count, n square or 2n square. So there are many different axiomatizations of the notion of a space in mathematics. Like, for instance, there are topological spaces, there are metric spaces. At the end, it all doesn't matter as long as one only considers non-pathological examples. It all comes to the same thing. So I will assume that there is some intuitive understanding of what space is, that some such understanding is present. So if one wants, so any space, if you formalize it, really write down a definition, it will be a tremendously infinite object. So it's very difficult to work with. So to distinguish spaces mathematically, we use what we call invariance. So something more understandable, more finite, typically, than the space itself associated to a space. So there are 2 invariants which I will dare to call the most fundamental ones. One is the dimension of a space. So we have dimension 0 for a point and dimension 1 for the interval. And another invariant is the number of pieces the space consists of. So in this picture, again, the point consists of one piece. You cannot divide it into two disconnected pieces. And then there is something drawn below the point, which is sort of a deformed circle with some deformed interval sitting inside, but it consists of two different pieces, two disjoint pieces, this circle and this interval. The number of pieces is another invariant of a space. Typically, when one thinks of a space, one thinks of a space which has only one piece. But that's just a custom. So what is homotopy theory about? What it does, it basically studies, I need to say something. Let's call pi 0 of a space the set of its pieces. So if space has two pieces, then pi 0 is a set of two elements, namely these pieces. So it's typically much more finite than the space itself. What homotopy theory does, it studies some fancy versions of this invariant, which are called higher homotopy sets. Now, I will try to explain how one gets to this pi n's, where pi n is will be some set for any integer n, for any, non-negative integer n, how one gets to pi n from pi 0. So the first thing which I need to, it can be done in different ways. So I choose to base my explanation on the notion of a continuous map, which will also play a fundamental role further. So what is a continuous map? So I have a space. This I cannot show on the projection. I have a space n, m, and the space n. And a map from one to another is any rule which assigns to a point of the first space a point of the second space. The easiest way, of course, to understand it is by looking at examples. And the idea that it's continuous means that if something was close, then it doesn't get too far apart. So let's denote by C of m, comma n, the set of all continuous maps from m to n. We'll see again by example what it is. If I'm looking at continuous maps from a point to any space, so what is a map from a point to a space? It's just determined by where this unique point goes. So a map from a point to a space is the same as a point on this space. So the set of maps from the point to any space is just the set of points of this very same space. Another example is what is the set of maps from any space to a point? There's only one place for all the points of the first space to go, namely this only point on the target space. So there is also always only one map from any space to the point. So that's example number 2. Here is a more fancy example. Let's look at maps from the unit interval, the interval of the real line, to any space. So it will have some beginning where the point 0 goes and some end where point 1 goes. And then there will be all the points where all the numbers between 0 and 1 go. So the fact that it's continuous map means that this gadget will have no breaks in it. That's what it intuitively means. So the set of all continuous maps from the interval to any space is just a set of paths inside this space. Now let's go back to the notion of the number of pieces of a space. How can we say formally when two points lie in the same piece? So if they lie in the same piece, then they can be connected by a path. If they lie in different pieces, there is no way you can find a path without breaks which connects one point to another. So to define formally what it means for two points to belong to the same piece, one can use this notion of a path, of a continuous map from interval to the space. So let me repeat myself again. So the only thing which one needs to know to define the set pi 0 of n, the set of pieces, is to know what are points and what are paths between these points. Well, this is a little bit more fancy, and maybe I'm not able to explain it as good. Now here I'm moving to the next invariant, next homotopy set, pi 1. As I said, pi 0 is the starting point of an infinite series of homotopy sets. So what one does for pi 0, one takes points and identifies sort of those which can be connected by a path. Now, suppose I fix 2 points, P and Q. Now, let's consider all the paths which connect them. Suppose they lie on the same piece, so there is some path which connects them. Let's look at all paths. So we get some space of paths, whatever that means. Let's try to understand how many pieces this space of paths has, and call this set of pieces the pi 1 of my original space relative to points P and Q. So in practice, what one has to do is to consider now continuous maps from a square. If I have a square mapping to the space, and let's say I request to have a map which contracts this side completely to point P and this side completely to point Q, then the image of this side will be a path going from P to Q, and the image of this side will also be a path which is going from P to Q. And as I move from this side to this side continuously, I can think of it as being a path between the paths. So it's continuous deformation between the paths. So it generates, now I can consider the set of pieces of the space of paths where 2 paths are declared to belong to the same piece if they can be connected by such a map from a square. Now, this is a procedure which can be repeated, and then I can use cubes to connect maps from squares, and so on, and one gets a sequence of sets, which are called homotopy sets of a space. Now, well, I'm sorry, that's what I just said. There is one nice example which I want to give. If we try to define these homotopy sets for the space of complex matrices with determinant, with a non-zero determinant, it's of course a very complicated problem, how to compute such a weird thing for such a weird space. However, it turns out that it can be done, and the answer, at least when we consider matrices which are very, very big, n by n, where n is very large, answer turns out to be wonderfully simple. It's the first homotopy set is the point. Any 2 matrices can be connected by a path, so there's only one piece in the whole space of matrices. If I consider paths, then it turns out that number of the pieces in the space of paths are numbered by integers. So pi 1 is a set of integer. I'm sorry, did I made a mistake writing this page. It has to read like this. Pi 0 is the star. Or did I? No, sorry. So pi 1 is then can be identified with the set of integral numbers. Pi 2 is again just one point. Pi 3 is again the set of integral numbers. And then it goes on like that for a very long time. For how long exactly depends on number n over there. But basically, if n is infinity, then it goes on forever. And that's called Watt periodicity theorem. That was one of the very impressive achievements of mathematics in early 60s, late 50s. I don't know the history well enough. But that was one of the really first big computations of homotopy theory. So that's what I wanted to say about homotopy theory. It studies spaces. It associates to them with homotopy sets, which come from studying paths of paths and so on. And here is an example of a computation, that these are actually things which can be computed in some non-trivial cases. Now I want to jump somehow and do something similar in algebraic setting. So there is only of one way to do it, and I don't know how much I will have time to say today, but there is one topic which I want to talk about very quietly and without hurry. So that's something which is, I never saw it even mentioned in any popular book about mathematics. I saw algebraic equations mentioned. I saw homotopy groups probably even mentioned, especially for elementary books in topology. But I think that at the heart of 20th century mathematics lies one particular notion, and that's the notion of a category. So let me try to explain what it is about. So it's a very formal gadget. And I will illustrate it by an example. So here are two examples of categories. Let's forget about the second one for a moment. Just look at the first one. So here I have a picture of a category with three objects, A, B, C. Now there are arrows between those objects, which are called morphisms. And then there is the rule, which says that if I have one arrow and then it's followed by another arrow, then there is a third arrow. Let's say if I have an arrow from A to B and arrow from B to C, then there is a rule to get from such a pair an arrow from A to C. That's called the composition rule. But let's even forget this third part for a second. It's not necessarily important for intuitive understanding. Main thing which exists in categories, so there are objects and there are morphisms. There is a formal set, in this case the set of A, B, C, which is called the set of objects. For every pair of objects, there is another formal set. In this case, it's X and Y between A and B, Z between B and C, and T between A and C, which are called morphisms between these objects. Now, the first example is an example of a combinatorial finite category. Here is a second example. Objects are spaces, all spaces which exist. Morphisms between two spaces are continuous maps between these spaces. And of course, continuous maps can be composed. So that gives an example of a category of a very different kind. And what was somewhat amazing for me personally, an amazing discovery, is that almost, let's say for very many classes of mathematical objects, there are natural categories which correspond to them. So for most classes of mathematical objects, we can construct a category whose objects will be these objects. Morphisms will be some natural ways of connecting one object of this type to another, and there will be some kind of composition. So sorry. So here is a more formal way to say what a category is. So there is a set of objects. For any pair of objects, there is a set of morphisms from this object to between these two objects. And then there is some composition rule. Now, what what I hope to do now is to show how such a, well, let's see how does it work. Why is it interesting? Let's, for instance, consider the category of topological spaces. And let's choose a space N. What can we say about this space? Looking at it exclusively as being an object of the category of spaces. So I don't want to look the inside of this space. I know nothing about its insides. I only know continuous maps relating this space to all other spaces. So instead of looking on the structure of the object, you look at his sort of social relationship. The very first example, can we figure out when the space is a point? And to this, there is a nice answer. The space is a space is a point if and only if, for any other space, there is a single morphism to this one. So that characterizes the point completely, exclusively by morphisms to and from it. Let's ask a more complicated question. When is a space N connected? So when it consists of only one piece. Or more generally, can we somehow express, let's say, the very first homotopy set, the set of pieces, purely in categorical terms? It turns out that, yes, we can. So let's try to play this game. So first of all, we know what is the set of points of the space. It's the set of morphisms from the point to this space. And we have already characterized the point in some internal way. Now, let's consider the unit interval. The set of maps from the unit interval, morphisms from the unit interval to the space, is the set of paths. Now, I need to know what is the beginning of the path and what is the end of the path. For that, I need the notion of a composition of morphisms. So if I have a path, I have two distinguished points, 0 and 1, on the unit interval, which are morphisms from the point to the unit interval. If I look at the composition, my path composed with one of these points, I get a point of the space, which is the beginning or the end of the path. So using purely the structure of the category, I know what is the set of points, I know what is the set of paths, and I know how to assign beginning and the end to a path. So now I can say what is the set of pieces, because it's simply, I have to identify 2 points which can be connected by a path, in other words, for which there is a path such that it's beginning and end, and that gives me the set pi 0. So the only thing which is here, which is not internal to the category of categorical structure, is the unit interval itself. We don't know how to characterize it from the inside. But as soon as I have a category and something which I want to call the unit interval with 2 maps A and B called beginning and end, I can define some kind of pi 0. How good this definition will be, it's a big question. So similarly, if I want to compute the next homotopy set, here I'm not going in that much detail, but what I will need to know will be, so the object point, the object called unit interval, and then I'll need to know to have some distinguished object which is called the square. And some finite number of morphisms connecting these objects. As soon as I have such a purely combinatorial structure inside my category, I can consider morphisms with values in any object and get something which I will call pi 0 and pi 1. I can continue that and model formally in any category. Basically, for what I'm talking about, it's enough to understand pi 0, and the rest is just not to look too elementary. So one can formalize the situation when one has point, interval, square, cube of the next dimension, and so on. Now, all these things in usual topological world map to each other. There are two maps from the point to the interval, the beginning and the end. There are four maps from the interval to the square, the four sides of the square. There are 6 maps from the square to the cube, the 6 sides of the cube, and so on. They satisfy some relations. So I can formally say, let's take any category whatsoever. Let's take a series of objects and morphisms between them satisfying appropriate conditions. Let's call such a gadget a cubical object. So as soon as I have a cubical object in any category, I can play the game which I sort of explained for pi 0 and pi 1 and define some kind of homotopy sets for any other object in this category. Of course, it needs to be said that in most cases, this is not going to work very well, but it will work somehow. Now, let's go to the next. Sorry. So, of course, that was just an example. In principle, there are many more structures, let's say in topological spaces, which are related, which are needed for homotopy theory. So one can translate most of these structures into categorical terms, as I tried to show on this example of cubical spaces. And then, as soon as they're translated into these formal categorical terms, one can try to take some very different category and apply it there and see what happens. So Motivic homotopy theory happens when one applies this kind of procedure to the following category of algebraic equations, which I will, systems of algebraic equations, which I'm going to describe in a moment. That's not exactly the standard approach to algebraic geometry, but that's the most elementary one which I could think of. So let's consider the following objects, which we call systems of algebraic equations. So by definition, a system of algebraic equations is the following gadget. It's first of all a list of letters, which are called variables of the system. And second of all, some list of polynomials in these variables, which are called equations of the system. So here is an example. There is one variable x and one equation x squared plus 1. Here is another example. There are n variables x1, xn, and there are no equations whatsoever. That's a very important system, which is denoted by an. Here is a more sophisticated example. I'm sorry, I was getting late writing it, and it's not probably very readable. I have, as variables, I have n square variables. I'm thinking about them as about entries in a matrix, plus one additional variable, which I call t. And I have one equation which says it's the determinant of this matrix times t minus 1. Well, it doesn't say anything, but that's my equation. That's my polynomial. And such a system of equations I want to denote by gln. Now, let's define morphisms. Oh, I need to say something else. So now I want to try to define the category of systems of algebraic equations. So what I need first are objects. And as objects, I want to sort of say, let's consider all systems of algebraic equations. But that's a bit too many. So a typical approach is we first choose what kind of coefficients are we going to consider. So we take some system of coefficients, integral numbers or real numbers or complex numbers, and consider all systems with coefficients in this type of numbers. That will be the class of objects of our category. Sorry. Now I need morphisms from one system to another. So I tried to write it down, and it's difficult to read on a projector. So by a morphism, I want to mean a change of variables. So a morphism from one system in variables x to another system in variables y is going to be some way to express variables y through variables x such that the equations sort of are satisfied on both sides. There is some obvious way to compose these things. It wasn't I who invented this. I don't know who invented it, but I read it in a wonderful textbook by Manin on algebraic geometry, which was published in Soviet Union in the end of the 60s. So here is an example. Let's consider A0. So remember, A0 is, let me do it this way. A0 is a system of no equations and no variables. So a morphism from such a system would mean that I have to find expressions of my x1, xn in terms of no variables whatsoever. So it means I have to replace them by constants, and the equations still have to be satisfied. So such a morphism is exactly a solution of my system of equations. So morphisms from A0 to x are solutions of the system of equations. Similarly, one can verify that morphisms from x to A0, there's always only one morphism. So these objects AN, these systems sort of with no equations, they form a cubical object in a very naive sense. One can easily build all the maps which exist between usual cubes. One can build them between these systems. And so I can use this cubical object to define some kind of homotopy groups for any system of algebraic equations. In general, I will get homotopy sets. In general, I will get not quite correct results. But there is an example. If I apply it to the system GLN, I will actually get very, very reasonable things. I will get sets which are called algebraic K groups of the original system of coefficients. And that these groups were defined in many difficult ways over the last, I don't know, 40 years. And they're still a source of great many interesting mathematical problems and insights. This is something which really depends on K. So for integers, it will have something to do with number theory and arithmetics. For complex numbers or real numbers, there are connections with special functions such as polylogarithms and hyperbolic geometry and I don't know what else. So these are very, very interesting groups. And sort of this is an example of how such a game can lead us to actually objects which are of independent interest. So now let me have the last slide and get a little philosophical. And so that's how I see the whole picture. That we start with geometry, category of topological spaces. We invent something about this geometrical world using our basically visual intuition. The notion of pieces comes exclusively from visual intuition. We somehow abstract it and rewrite it in terms of category theory, which provides this connecting language. And then we apply it in a new situation. In this case, in the situation of algebraic equations, which is purely algebraic. So what we get is some fantastic way to translate geometric intuition into results about algebraic objects. And that's from my point of view, the main fun of doing mathematics. Thank you.